Next, Takayuki, Professor Takayuki Nagai.
Okay, thank you very much, Shima Sensei. Thanks for your very nice organization of this roundtable. Let me share my screen. Can you see my screen?
Yes.
Okay, all right, let me start. Thank you very much. My name is Takayuki Nagai. I'm a professor at Osaka University. And let me briefly introduce myself. I'm in the research direction. So needless to say, we are interested in cognitive robotics, which is a kind of constructive approach. And what we want to do is to know human intelligence, why it's so flexible and very high level. We can do high level inference and so on. So what we do is to construct the human-like intelligence using robots, and then try to find out the mechanism behind that. So the important thing is that science actually decomposition process, and engineering is kind of construction process. So these two must be a kind of complementary process, and what we have to do is to make a kind of loop between these two. I mean, science and engineering. Of course, application is also important, but the basic motivation of our research is to know what is a mechanism behind our human intelligence. So in the sense, I'm looking at the way to integrate as a whole. I mean, we need to do the integration of motor control, language, inference, causality, creativity, and so on. So in order to do this, we are using actually real robots, and also we are building some kind of machine learning model for mimicking the human brain, I mean the cognitive functions, and we call the model as integrated cognitive model, or a recent trend in AI is this kind of model is called world model. So this is the basic idea that the model is actually model consists of the representation. We actually use the hierarchical Bayesian modeling, but we can do exactly the same thing by using the deep generative model. But anyway, the model is actually consisting of representation and also reinforcement learning in order to make decision, and also kind of the model for sequence or temporal information. And also this model actually includes some language learning part. And yeah, latent variable. This is a kind of, we hypothesize that this latent variable actually correspond to the kind of concept of our intelligence. And we actually build this kind of model and implement this model on the real robots, and have carried out a lot of experiments. And maybe I don't have to say anything about this, but this is a kind of sensor motor loop. And I'll show some recent experiments. And this one is almost 5 years ago, but my student actually interacts with this robot. This is a kind of baby robot. You cannot see this, but anyway, we implement the model as I explained on this robot, and use about 500 objects that student actually interact with robot for about 1 month. And finally, so actually the student is a kind of parent of this robots, and try to make the robot learn the language. So the result, I'm not going into detail, but the robot actually learned around 500 words, which correspond to like a 1.5 year child from scratch, I mean. So, and we actually compare with human child, it's actually really hard to fair comparison with human child, but we found that the robot can learn in a similar speed with a human child. There must be, of course, there are a lot of similarities and also dissimilarities, but we actually analyze the concepts that the robot acquired and the human concept. For instance, the concept of color is really easy to analyze, both for human and robots. So we compared with these two and found a lot of similarity between these two. And recently, what we are doing is to apply this kind of world model to home service robots. What we doing is the use of teleoperation. I mean, the teleoperator actually teleoperate these robots in the real home environment, and then the robot can get a lot of data, and then robot actually learn how to do in that situation. I mean, how to tidy up the messy living room and something. This is what we call learning from teleoperation. And yeah, basically the setting of the home is not the very real one, but the robot actually tidy up this kind of, like this is not the real one, but this kind of, messy room can be cleaned up by the autonomous robot. And finally, I'd like to summarize by saying some kind of, what is a challenge? And I think of course, there are a lot of things, but we need to think about the communication. Like right now, our model doesn't include some, self-other discrimination stuff. So we have to implement some, kind of functionality of mirror neuron system in order to learn the self-other discrimination for communication. And also, I think it is very important to think about the emotion or affection stuff. Recent emotion studies revealed that the mechanism behind emotion or affection. So the important thing that in the emotional study that they said that interoception, which is information on our own body, is very important. So we think that we can implement this kind of, robotic emotion on the real robot. And also we have to think about the higher level cognitive functions like logic system and causality, counterfactual processing, explainability, and creativity, and so on. And the hardest problem is to understand what is consciousness. So I'm not sure how to do it, but we have to think about how we can implement or make the robot some kind of consciousness by using the research of cognitive robotics. So that's it. Thank you very much.
Okay, thank you very much, Professor Nagai. Yeah, this is very interesting, and I think that the generalization program is very important topic in the discussions. Thank you very much.
Thank you very much.